fact, if you do this circuit without that extra Hadamard, zeta plus 0 becomes 0 plus zeta. So this, with a plus here and the 0 here, swaps the zeta down here. So this just teleports the zeta there. So you can see this does teleportation. You need to check that this entry comes down here. And you also need to check that this entry and this entry are constant, independent of what this guy is. Because if they weren't, then this state would be entangled with these states, and it wouldn't be teleportation. Well, it's fairly easy to show this. I mean, what you need to do is, zeta equals alpha 0 plus beta 1. So let's look at what happens when we put 0 plus 0 in. 0 plus 0. Well, the first thing we do is a control knot here. And that's 0. Well, wait, no. There's an easier way of thinking about this. Well, this control knot does nothing because the top state is 0. And here we apply a control knot and we apply another control knot, so that does nothing as well. So the only operation here, we have a 0 controlling knot into another 0, which gives us a 0. So 0 plus 0. Now the next one is a little more complicated. 1 plus 0. So after this, the state is 1, 0, 0 plus 1, 1, 1. And now we're doing that. Well, what does this do? It control knots, or XRs the first qubit into the second qubit. So after this guy, the state is 1, 1, 0 plus 1, 1, 0 plus 1, 0, 1. And now we do that again. So it becomes 1, 1, 1 plus okay, I'm running out of room here. So, but you can see that here it's 1, 1, 1 plus 1, 0, 1. And the last thing is this guy. So what that does is take the last qubit and XOR it with the first qubit. So that becomes 0, 1, 1 plus 0, 0, 1. And that's here. And this is 0 plus 1. So 1 plus 0 became 0 plus 1. And now the last thing we get is a Hadamard and a measurement. So you can see that both of these states are plus right before they're measured, which means all measurement values are equally likely. And if you go back to our teleportation circuit, or the first way of analyzing teleportation, you would have seen that all teleportation values were equally likely. So that is the way of using the circuit to analyze how to teleport, to show that this teleportation circuit actually teleports the first qubit to the last qubit, which means that the original teleportation circuit, which I've now erased, also did. Okay, that's, yeah?
So the measurements are just there to tell you what you teleport?
Well, the measurements are necessary in the original teleportation circuit because, well, you need to get information from Alice to Bob somehow. And in teleportation, they don't have a classical channel between them. So the only thing they can send is classical information. So let's write down the original teleportation circuit and go over it. So we had psi plus 0. Measurements. And let's see. So this first thing is done before these 2 qubits get distributed to Alice and Bob. So Bob owns everything here, and Alice owns everything up here. And the only thing going from Alice to Bob are these 2 green classical bits. So Alice and Bob are in 2 different labs with a classical telephone line between them over which they can send classical bits. So the reason you did this measurement was to convert the information into classical information, which then can be sent to Bob over a telephone line. Or, yeah?
So in the idealized version of the circuit, these measurements are no longer necessary?
In the idealized version, oh, you mean in this, yeah, in this version of the circuit, you don't need those measurements.
Okay.
Yeah. But I kept them because they were in the original version. And I also wanted to show that this circuit made all 4 measurement outcomes equally likely, which was necessary for the original teleportation. Good question. Yeah?
Sorry, just one last question. For the circuit that we have on the top right there,
Yeah.
if we start after the first C naught, it looks like the operation that we're describing is like a totally non-local thing between Alice and Bob, right? It's just some unitary that has these like that control Z gate, which is a non-local operation.
Right. So this is a non-local, so this and this are non-local operations between Alice and Bob.
And yet it turns out you can do the same thing with just local operations in classical communication.
Right.
And so if someone just hands you a unitary, is there some way to tell whether or not that can be done?
Well, the only reason we could do that, really, is these 2 measurements afterwards, which we could commute back over this gate and that gate.